So what I want to do today is finish talking about this column count idea, and then put it all together and show you how the Sparse-Cholesky factorization works. So we left off with this column count idea, and so here's the key thing again. We've got already we can remove out and just add the entries in the skeleton matrix, because we know that because they're a leaf in the skeleton matrix, they will not appear in any of the children of node J, because if they did, they wouldn't be a leaf. So then we need to take out the union of the children. And then, so to do that, we have this notion of, well, first we can say, well, let's just look at taking out each child itself here from each child, and so that's the subtraction here. So this is just simply the number of children a node has in the elimination tree, and that's easy to find. That's a static number. It's based on the entire tree, and now we just have to find the union of all the children. And so this then splits up into this: the sizes of all the children plus how many times any element would appear once or one or more times in the set union. Okay, and so what I showed you then were three different cases as to how to compute that. So we have the tree T sub I, and we have J. Okay, well, first of all, I mean, I've already drawn it where J is in the ith row subtree. If J is not in the ith row subtree, even if J is a descendant of I, if it's not in the ith row subtree, then it won't count to the overlap at all. So it's not in it. So there's nothing to do. If it's a leaf, then it's in the skeleton matrix, so there's no overlap. There's nothing to do. So that's a special case. So basically, what we have to do when we've done this computation, we find this overlap. We have to do two things. We have to say, well, if J is a leaf in T sub I, and then we know where that is because of the skeleton matrix theorems, then the column count for Cj is just the size of the skeleton matrix. I'm sorry, leaf in the entire tree. If it's a leaf in the entire tree, then we just have to add in the size of the skeleton matrix, plus 1 for the diagonal. Okay. And then, if it's not a leaf, we've got to find these correction terms. So this already assumes here that I've got a node J which is not a leaf the entire elimination tree. I've got children here that I have to take the union of. If there's no children, then this is just the size of the skeleton matrix plus 1. So then the idea here is that we could have a node J. So that was the first case. The first case is not a leaf that it's a leaf in the tree. And the second case, that's the first case. The second case is it is a leaf of the ith. It's a leaf of the ith subtree. Okay, so there's no overlap in row I, because if I look at the ith subtree, if I have a leaf here, then the first, basically, we could have children in the tree here, but none of these children can include row I itself at all. If they did, they would be in the ith row subtree. So I will not appear here. Down here, there's no I in the entire tree. So if J is a leaf, well, then I just appears once in column J. It won't appear in any descendant. It just appears first in column I, and that will be thus in the skeleton matrix, and so there's no overlap to worry about. And then the other issue here is if J is up here. Now there's two different cases. We can have children of j in the tree and children of j outside the ith subtree. And suppose I do this. So j can have multiple children. J can have, in this case, 5 children, say. Okay. 3 of which are in the ith subtree and 2 of which are not. Well, these 5 children are the entire set of children in the elimination tree. And so Lj will be the union of those 5. Those 5 L's. Okay. But 2 don't have I at all. There's no I, row index I in these columns here for these nodes because they're not in the ith row subtree. Just these 3 will have that. So those are the only ones we need to consider. So there's 3 to consider. I should have picked a different number here. Maybe I'll make this 1. So there's 1 that has nothing at all. There's 3 to consider. And so the overlap here, I guess, I'm trying to come up with unique numbers so there's no confusion. The overlap here is 2. So these are just completely ignored. I could have 27 children out here. Why don't I just put a whole pile of children there? 4 children there. 4, so I've got 7, just to make these numbers distinct so they're not confused. So I have 7 children total, 4 of which are not in the ith row subtree, so there's nothing to do with those at all. And then in terms of the overlap, okay, there's 3 of these nodes to consider. Then 3 of them will have it. 3 of them will have row index I, and so the overlap for column J, considering just row I, will be 2. And so to detect this, then we have to ask the question: if I've got J here, and it's not a leaf, and it has 3 descendants, 3 children in the tree, the ith row subtree, then these must come to an end at some point. Okay, I've got to stop somewhere at a leaf. So if I go here and I go down to a leaf, this must be a disjoint path. I must have exactly three disjoint paths, all of which merge at J, in the ith row subtree. And if I have 3 disjoint paths, all of which converge at J, then I've got 2 pairs of adjacent leaves. Well, there might be, let's see, there might be more leaves. I mean, they don't have to be adjacent, I should say, because there could be another path here, for example. Okay. But there are 2 pairs of leaves. The key point is that there's a pair of leaves here for which I find J to be the least common ancestor. And then there'll be another pair of leaves, maybe not the next pair, could be this pair right there. But there'll be another pair of leaves, whoops, no, this will point to here. There will be another pair of leaves whose least common ancestor will be J. So it'll appear twice. So the least common ancestor of J, the least common ancestry of 2 nodes will pop up and say J twice, exactly twice. So that's all we have to keep track of, is how many times that occurs. So all these different terms can be combined into a single correction term. And that's what I'm getting at here. If J is a leaf of the elimination tree, it won't appear there won't be any overlap, there won't be any children. So I need to initialize the since there's no children, the total column count is just all of delta J, which is just the size of the skeleton matrix plus 1. Which is then going to be the entire column A. This will be equal to, in fact, the entire column. Otherwise, this correction term, but I'll just keep track of this as the skeleton matrix as we go along. But otherwise, the correction term is the size of the skeleton matrix minus the number of children minus the overlap. So what we need to do then is and then once these 2 are computed, I guess I don't have to write this if and else that's right up here. Once these 2 are computed, then all these correction terms are folded into one case here for any column, whether it's got children or not. So it's these delta terms plus the sum of the counts of the children. This is easy to find after the fact. I mean, if we just find all the delta terms, okay, then we can apply this formula recursively, just going up the tree. In fact, going from left to right, going from node 1 to node n, if it's in post-ordered fashion, because if once I compute all the s will be less than j here. The children are always numbered less than j. So this computation is easy to compute if I just have all these delta terms. So the delta terms are two things. It's either this or this. And so what I have to do then is, and I've got an example here for column 4. It appears it has column 4 has 2 children and the overlap is 2. So the delta term is minus 4. And if we add the sizes of its 2 children, we get 7, but we subtract out 4 for the correction, we get 3 as the column count. So now it boils down to finding this delta term. So the delta term initializes in 2 different ways. If it's a leaf of the tree, we're going to be counting this skeleton matrix. We don't know what the skeleton is. Right? We've got to do that first descendant and max first and all of that. As we process the tree, we'll find what the skeleton entries are. So we're going to count each of these one at a time. But if it's a leaf, then I need to initialize delta to 1. Otherwise, I'll initialize it to, let's see, either 0, and then I'll count the children. I forget which I do. Or just initialize it to the negation of the number of children. And then count the skeleton, and then decrement every time I see an overlap, which is the number of times j appears as the least common ancestor. Okay, so anytime I see j as a least common ancestor, delta gets decremented for j. And then when we're done, we just add up all the deltas. And so, let's see, what does that do here? I initialize delta to... Yeah, okay, so let's look at the algorithm now. There's some initializations here which I'm going to skip for the moment. Just like the row count algorithm, and I'll come back to this. When we do LU and QR factorization, we'll come back to this. But it turns out you can also, I've focused so far on analyzing a matrix A and doing its Cholesky factorization. But there's some cases when we want to do look at the Cholesky factor of A transpose A, and I'll explain that when we get to LU and QR factorization. The reason there is because the Cholesky of A transpose A governs the pattern of the matrix U for LU and R for QR. But I haven't talked about LU or QR yet, so let's just skip over this. But I just wanted to point this out that here it is, but we're going to ignore it. But so ATA is going to be false, and so the head of KJ will just be J, and the next will always be nothing. Okay, next of J will be nothing. So when you see down below a thing, head of, it's just a linked list. It's going to be a linked list that'll form here, but in the A case, the symmetric case, J is just J. So if I start at a head of K comma J, I'll just find J itself. I won't use this head and next at all. But this initializes head and next for the A transpose A case, but it gets skipped entirely if A transpose A, ATA, the flag ATA is false. So we come in here, so ignore the head and next thing in here. Right here, head and next are just null by default. And so we've got some workspace here. We've got delta and column, the output column count. This is what's going to be returned at the end, is the column count. The column counts can actually be aliased to delta, because delta is just going to be overwritten with the column counts when we're done. So that's the output, and then this is workspace here of size 4n, basically. And that's going to be that's going to be the max first. So to keep track of the skeleton, that's going to be the previous leaf to keep track of where the pairs of leaves are. It's going to be the ancestry shortcuts, so that's 3n. And then I need, let's see. Ancestor, max first, previous leaf, and then first. Yeah, the first descendant of every node. So that's, wait. Oh, I'm sorry, that's 5n. Yeah. Wait a minute. S is of size 4n. 1, 2, 3. 1, 2, 3, 4. I can't count. That's 4n workspace. Ancestor, first. Yeah, delta and column count are alias the same, and that's the output. They're not in the workspace. So max first, previously first, and ancestor are four workspaces. And just to keep things simple, I just set the whole workspace to -1. I don't actually need to initialize it all to -1, but just set the whole thing, in all 4n. This is overkill here. And that mostly has to do with, I need to initialize first, and also, let's see, previous leaf needs to be initialized to -1 as well. These two have to be initialized as empty because I need to know that it's not yet computed. And here I need to know that there is no prior leaf. So I set it to -1 in all the works. And the ancestry I'm going to initialize separately. The same thing with the max first. Actually, max first could start out as that. I think that needs to be -1 as well. So initialize the workspace. Then we find the first of each. This is finding the first descendant. Okay, we've seen this algorithm before, but I'm adding to it now. But I'm not calling the previous code, but I'm just incorporating it here. It's slightly different. Again, we're viewing the matrix through a post ordering. So there's a remapping from K to J. So if you want to ignore this and call K and J equal, that's fine. Just imagine that it's post ordered. Then we need to initialize delta to be either 1 if it's a leaf or 0 if it's not. And it's at this point that we can detect, because we're computing the first descendant of every node in the entire tree. So we come to a node and ask, well, has the first been computed already? If it's not been computed, then it's a leaf of the entire elimination tree. So delta is equal to 1. Then, if we have a leaf of the elimination tree, we need to pick that leaf and walk all the way up the tree until we find a node whose first descendant has been computed and set that first descendant equal to this leaf J. Or K, I'm sorry. K is in the post-ordered fashion. So J is not post-ordered, but K is. So, because the tree, the node names are all in the old space, but the first has to be in the new space. Okay, so now we've got to start off this ancestry idea to do the shortcuts for the least common ancestor. So we've seen that before. I did that with finding the least common ancestor computation. And then the next page, and this is the last of it, just has to walk through, well, no, it's not the last of it. There's a function here, CS leaf. So we have to walk through and every node, and then we need to adjust delta. So remember this delta thing we're trying to compute. If J, so I've already done this. I've added the 1 here for the case where J is a leaf. Otherwise, C of J, let's see if I can remember, is the size of the skeleton matrix minus EJ minus OJ. So this means I need to decrement every time I see J as a least common ancestor of any pair of nodes at all. And here I need to decrement delta for every child, every time I see a child of J. I could have a separate pass that computes that, but this line of code does it right there. I'm going across all the nodes anyway. If I see a node that has a parent, decrement, I know I'm a child of my parent, so I decrement delta of the parent. So that's the way. So this one line computes this piece of the delta I'm sorry, this is the delta delta J, not Cj. So they're summed up then later. So this is the term I'm trying to compute for every J. And so this one blob there is this statement here. Okay. And then I need to increment delta J. So there's three places where I need to modify delta J. Once when I find that it's at least common ancestor. I'll increment it every time I find J in the skeleton matrix. And I'll decrement every time I find that J has a child. So here I'm at a J, but I'm decrementing the parent because I see that the parent has the child, namely me, J. Okay. So now for the symmetric case, just capital J is equal to J. So you can ignore this. And then this computation here is not going to do let's see, ATP is, and ATI is just the A matrix. I'm sorry, AT is transpose. I have to transpose the matrix because I'm wanting to go through, let's see, I need to go through this. So I'm going through these entries here. And why do I transpose the matrix here? Let's see. I need the transpose for the A transpose A case, for sure. And so it just simplifies the computation just to do it here. Why do I need to... If the matrix is symmetric, could I have skipped that? Let's see. The algorithm is operating in, and this is from the MATLAB convention. And it's also because of the way my numerical factorization works. I'm only looking at the upper triangular part of A. And I'm completely ignoring the lower triangular part completely. So I'm assuming that the matrix is symmetric without even looking at it. So since I'm looking at the upper triangular part, but it's stored by column, if I look at this column, I'm not going to find entries in this row. I'm not going to find entries in this column. I'm effectively looking at the lower triangle, but I need the lower triangular part here. So if I have just the A matrix and I only want to look at the upper part, then in fact it's this piece right here is actually that piece. So it's the wrong piece. So I need to transpose it to get the lower triangular part of what I want, which is the transpose of the upper triangular part. So then this is going through then every entry in the column, and it's going through, and I don't have to check to see if it is, but I'll check later to see if it's in the upper triangular part. I skip it. So I grab out the row index, and then I do the leaf computation. I want, this is going to answer my question. And we've seen this function before. It's going to answer my question: is this a leaf of the ith row subtree? Is J a leaf? It's going to ask the question: is J a leaf of the ith row subtree? And to do that, it needs to use the first and max first. It's going to update max first. Once it finds a leaf, it's going to keep track of the previous set of leaves. This is going to get updated. And it's going to update the ancestry information for the least common ancestry. And then it's going to return a flag that says, are you in the skeleton matrix, or are you in the skeleton matrix, and are you a subsequent leaf of the... And if you are in the skeleton matrix, so there's three different cases. First of all, J could be not in the skeleton matrix. J could be a leaf of the skeleton matrix, and that would be the case here. Or J could be let's see. Or if it's a subsequent leaf. So then the question is, if it's a leaf, what kind of leaf is it? Is it the first leaf, which in case there is no prior leaf out here? Or is it a subsequent leaf, in which case if there's a previous leaf, then it has some kind of common ancestor, Q. See, the first leaf doesn't participate in the least common ancestry computation. It's only a subsequent leaf here. So if J is any leaf at all, then I have to increment delta. So that's what's happening here. If J is any leaf at all, then I have to say, hey, you're in the skeleton matrix. Okay. And if J is a subsequent leaf of a pair of leaves, J and some prior leaf, which is hidden inside this function, I don't know which. I don't at this point know who it is. I don't care. Then it's got some common ancestor, and that's what Q is. So this CS leaf function is returning the least common ancestor of J and whatever previous leaf was found in the ith row subtree. So here's J, here's Q, and here I'm going to call this J previous inside that code, but I don't need to know outside that function what J previous is. But it's going to determine that Q is the least common ancestor. And it's then Q that has this overlap. So at this point right here, I need to decrement the overlap, or delta, for Q, not for J, but for Q. So this is doing the work for Q here, of its overlap, the overlap for Q every time, because Q has been found as a least common ancestor of a pair of leaves in the tree. So then, once that work is done, we've got to update the ancestry information, because we've seen this before when we went through the least common ancestor idea. And then that computes all the deltas. Once all the deltas are computed, then the delta and call count are actually the same. They're overlapped in the same array. And so then all we have to do is walk through the nodes J and compute that summation across all the. So the column count is your delta plus the sum of the column counts of your children. So what I do is I walk through all the nodes, and if I'm at a child, then I've already computed my column count. That would be a loop invariant here. If I'm a child of some parent, I've already computed my column count, and so I just need to then add my column count to the column count of my parent. And column count is initialized to delta because it's the same array. So that's what this line is doing. It's summing up delta plus the sum of the column counts of all the children of every node. And so then we're done. That's the entire analysis. So let's look at that leaf function again. We saw this before. I walked through it long before when we looked at the row count algorithm. We had this leaf function right here. We already went through this. It does the path compression of the ancestry jazz. It keeps track of whether or not it returns this flag that's either 0, 1, or 2. It's 0 if this thing should just be ignored altogether. It's ignored either if the entry is in the upper triangular part, or if it's not a leaf in the skeleton matrix. If it's not a leaf in the skeleton matrix, and there's nothing to do. Otherwise, we keep track of the prior leaf. So here's the previous leaf being updated for tree I, the ith tree, subtree. And then we ask, well, hey, if there's no previous leaf, then the flag is 1. It's the first leaf, and just return. Otherwise, we've got to do this ancestry calculation. We've got to find the least common ancestor Q, walk up that ancestry path starting at the previous leaf, walk up until we find the ancestor of that subtree, and then that must be the least common ancestor Q of both the previous leaf and node J. So that's putting it all together. That's a lot, isn't it? Okay. You've just then seen you've probably seen the thickest theory of the whole course. So if I know I'm going through it very methodically and very slowly, okay. But I think this is the reason I've taken my time with this is because it is the most difficult theory of the whole book. Okay, so it's all downhill from here. You've just seen the worst of it. All right, that was a lot of theory. Yeah.
A question about the ancestor array.
Yes.
In CS counts and in CS leaf, you're modifying that ancestry array, but in CS counts, it seems like it's
the call count.
Short, huh?
The call count. The CS call count.
Yeah. Sorry. It seems like that ancestry assignment you're doing right at the end.
Right here?
Yeah. Wouldn't that like short circuit some of your, or not short circuit, wouldn't it shorten some of the hops that you're making? That you like, because it seems like CS leaf you're finding some pretty big hops
right.
to ancestors, and then right here at the end you're just shortening right back to your parent. Like you're taking a long jump,
okay.
and then you're shortening it to a short jump.
Okay, so the question is, this seems like it's shortening our search. Actually, it's not. And what's happening is this. We're going through, so J is incrementing. J equals 0 to n minus 1, of course, in a post-ordered fashion. All right. And so whenever I ask, who is the least common ancestor of some previous leaf, some previous node, I'm always asking it with some J less than, or some previous node less than J, and J itself. Okay? And so I've not yet traversed the path for J at all. See, so I've got J here, and I'm trying to find Q, the least common ancestor. Okay. All of these, so this is J previous less than J. All of these nodes here, all of those nodes are less than J. See, I'm not traversing this path yet. I haven't traversed it yet. All I need to do is walk from here up, and I want to stop at that one Q, which is larger than node J. So, and I'm overusing J here. This is going to be a different J and a different Q. So let's just look at this picture here. So the paths starting from J have never been traversed whatsoever. Okay. And so you've not even seen that part of the array. In fact, this could have been done in a separate a separate loop outside. I could have had a separate for loop. But I'm just initializing it as I go, basically. J has no ancestor at this moment. So walking up here, and what's important to see here is that this is the Q that is bigger than anything seen so far, including J itself. So that's what I'm doing the shortcutting for. But when I finish this computation, okay, I have to, so this is all done. Now, when I look now at just J, so I've got some Q and some path here. Okay, so this is some node larger than J, Q bigger than J. Now when I come to, now I need to expand the tree. I need to expand this, not the tree if you will, I need to expand the space at which I've computed all the initialized all the ancestors. So I'm moving from here to here. And now when I move across here, I'm going to be finding all the least common ancestors of some nodes in this range and this node. So now the question is, how do I extend these sets to include J itself? Well, if you come down here, J has to be folded into with its parent. Because look what happens if J then appears as this node for some subsequent computation, this particular node. It's going to appear here now. Now I'm going to try to be finding the least common ancestor of some node J prime larger than this particular J. So here's where J was. And this is then the parent of J. Parent of J now is going to be the answer of, well, if I'm at a J prime, and if I walk up the path and I see J, either as if I start at J or I start at some descendant of J, I walk up and I see J. From J, I'll then walk to the parent, and then, oh, wait. That's going to be outside that's going to be one either equal to or one past J prime. J prime could actually be this node. Well, will it be? Let's see. No, it won't, because if that happens, J prime will not be a leaf of the ithro subtree. So J prime and Q and this node will be different. If this was J prime, it wouldn't be a leaf if you're traversing it. It'd be, right. So that's why then the ancestor of J needs to point to the parent of J. Initially. So this computation here, the ancestor, what did I initialize ancestor before? I don't think I did. Yeah, oh no, I set everybody to be in their own set. Let's see. There's an edge case here that has to be considered. So initially, everybody is your own ancestor. And then you're updated. So you're your own ancestor, and then when you finish J then points to the parent. Oh yeah, I know why. So the reason, so I did initialize ancestor. The reason here is that that simplifies the termination criteria. So I don't actually have to ask the question, do I walk past J prime? I just have to know, do I reach the end of the world? So this guy right here needs to point to itself. So every node beyond J prime, beyond the scope of which I'm computing for J prime, has to just point to itself so I know where to stop with this path traversal jazz. So I don't actually have to do the inequality check inside CS leaf. Up here, you just walk up and find your master. You don't actually have to know that, oh, this is the node that's bigger than J. Just walk up and at the point at which you get stuck, you stop. If Q is your own ancestor, you stop. So you go hop, 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 and then self loop, we're done. So that self loop tells us where to stop. Okay. And this just retraverses the same path. But this is the key point here. And it does the whole body of the for loop with just a single semicolon. There's no work to do. So you start at the distant leaf here. So that one for loop is starting here and it's going hop, 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 hop. Oh, I'm stuck. And that's the answer Q. The point at which you find the self loop is where you get stuck. And so this right here depends on the fact that initially ancestor of I is just I. So everyone has a self loop to themselves. Everyone is the terminal point of their own path. And then when J is finished, you don't want to stop. You don't want to ever then again stop at J. So when a node is finished, it always needs to go to its parent at least. Because you're always going to be wanting to find the least common ancestor of this prior node now, J, and J prime bigger than J. So you've got to stop at a Q. Well, it's going to be different like this. You're going to stop at a Q that's bigger than both of them. So if you're going to continue from J, you're not going to stop at J. You're going to keep going to its parent at least, if not farther. But it's basically starting the shortcut to say that I haven't traversed this path before except just the one edge. I've gone to the parent. And so that's my ancestor. Well, I haven't traversed it yet at all, actually, at that point. But when I do find it, when I do see this node again, it's going to be inside this blob here, and I want to go up and go to its parent, and perhaps stop there. So that's why it's not removing our shortcuts. We've just never walked that path before. Good question. Good question. Shows you're mulling over what it's doing. Yeah, you got to really just sit through this chapter and just draw out some pictures like I've drawn them to kind of get a grapple on why these theorems are working. I broke it up. I tried to break it up as methodically as I could in the book and also in the lectures. Okay, and in doing so, when I broke it up as methodically as I could, nugget piece by piece, bite-sized chunk by bite-sized chunk. Okay, here, what's the first descendant? What's of a node, and what's the level? How do we compute that? So that was a separate computation. Okay, what's the skeleton matrix, and how could we find that? Okay, piece by piece. I just didn't dive in to say, here we are, boom, here's the whole theory all in one place, and that's the skeleton matrix. Well, but you see now it's buried and jumbled with all this previous leaf and ancestry jazz, which is irrelevant to the skeleton matrix determination right here. Are you in the skeleton or not? This first and max first could be done independently of all the rest of it. Well, that's what I did. And then all this delta J and the column count adds to the row count. If all I wanted to find is the row count, I don't have to find this delta. I can just... The algorithm is much simpler. Let's go back to the row count algorithm. Oh no, I skipped it already, didn't I? Let's see, where am I? Yeah, the row count algorithm, you notice, is almost identical to the column count algorithm. I have this leaf computation. There's that same question you were asking about this statement. Okay. The only thing that was different with the row count algorithm is I just summed up the length of the path that I just traversed from the least common ancestor, from J to my least common ancestor of Q and the previous leaf, whatever that is. And I returned a flag saying, you're a leaf. So that was the row count. There's no delta in here. Okay, so this is almost identical to and this first descendant thing finds the first and level of every node. Now in the column count algorithm, I don't need to find the level. So there's no CS underscore in front of this. This is just a mock-up code. It works. But it's a stepping stone. Okay, so I tried to break it up into manageable chunks as much as I could, both theory and discussion in the book and also the code. So you can kind of see it developing incrementally. So I recommend you go through those. It took me, writing this book was a lot of fun. Have you ever heard the idea that a book just writes itself? This almost completely did that. I mean, I just sort of knew the storyline from the beginning, where I needed to go, where I put all the pieces, who the main character of the story is, this Oliver Twist, the sparse triangular solve. I wrote, the book is about 240 or 230 pages long. I drafted a fairly good draft of code and text and theorems and figures and everything in 4 months. I wrote 200 pages of this book in 4 months. I figured I was writing at the rate of, that's 50 pages a month. That's like 2 pages of actual finished polished text and code and debugged code per day. Right. So, and at some point I was working at 4 pages a day. It was just screaming along. Okay. And then I spent an entire month on about 10 pages. And you're looking at the 10 pages. Okay. Wrestling through, how do I most clearly describe all of this information here about the row and column count?
So did you write the C-Sparse package just for the book?
Yeah, I just wrote it for the book. Yeah, it didn't exist until I wrote it for the book. Actually, no, I take it back. I wrote 200 pages in 3 months. I wrote the whole book in 4 months. But it took me, one of those months was just this part, just one part of chapter 4. So I think in the other parts, for 3 months I was writing, almost 200 pages. I think it was 3 months. So it was like some absurd amount of, my poor wife, she was like completely neglected for those 3. She was a book widow. People who write books, their spouses know what that is like. It's very consuming, you're living and breathing it, and it's coming out your nostrils, and you just can't get away from it, and it's just. But this section 4.5 and 4.4, the column counts, 4.4 the row counts, and to some extent 4.1 computing elimination tree. These pages, of which we spent, this is like 10 or 12 pages in the book, 15 pages in the book. I spent a month writing this. So this was the slow part for me. Yes, and I wrote the code for the book, just for the book. I had written pieces of the code before in other algorithms. So I pulled some of it. I just pulled together and then pruned it down, simplified it, threw out stuff I didn't need, and condensed it and tightened it up as much as I could to make it as simple yet feature-rich as I could. So that gives us then this big picture. Back to the pulling back now, back to the big picture. I've got about a minute left, so I can do just this big picture. So what's the whole process of doing a Cholesky factorization then? Well, first of all, we've got to find a fill-reducing ordering. If we try to factor the original matrix, we'll have too many non-zeros in our result. I've not touched on how to do this yet, but I will. That's chapter 7, I think. Permute the matrix, and then we've got the matrix C that we're going to factor. Find the elimination tree, do the post-ordering, find the column counts, do the cumulative sum. This is like a one-line, the cum sum function. Accumulate, we've got the column counts, do a cum sum, and now that gives us buckets, if you will. The sizes of each bucket. Every bucket is a column of L. All right, you did this, you looked at this when you were looking at constructing a sparse compressed column matrix. What do you have to do is you have to go through count and then say, well, how many entries are in every column, and then lay out how big each column is, and then lay out the column pointers. All right, so I've done that here. And that's the end of my symbolic analysis. Now, other symbolic analysis sometimes actually needs to then go and compute the non-zero pattern of L. But I don't need to do that because I'm going to compute it on the fly. So what's going to happen here then is I've got these buckets here, one for every column, that are now empty. And now I'm going to fill these buckets one row at a time. So I'm going to compute the Cholesky factorization, not column by column, but row by row instead. And in doing so, then at the end of the day, all the columns of L will be sorted, actually, as a byproduct, which is kind of nice. But if I'm going to compute it row by row, I'm not going to need to compute this row. All I need is this part. And so I've got the values and the pattern of L computed already now. And then I just need to find the ith row and stick the entries then at the end of every bucket. And as a result, then, all the columns will be sorted. So that's what the numerical factorization is going to do. It's going to do this up-looking Cholesky factorization. It's going to use the sparse triangular solve to compute each row one at a time. Every row is computed as a sparse triangular solve. It'll find the pattern, so I'll know what entries to put, what columns to put row I in, and the values and what values to put there. So that's what that's what we'll look at then next class. So, and the project, by the way, I changed the date. I made a mistake. I said it was due the 11th. It's really due it's the 18th because I realized after I posted it, wait a minute, what about spring break? So it's due the 18th. So see you Friday. Thank you.